So, welcome back to the set of lectures about resistance and resistivity, conductivity, etc. etc. Okay. We had obtained from the analysis in the case of an electron gas model in a metal, the conductivity sigma was equal to n E square tau upon m, where n is the number of electrons per unit volume, E is the electronic charge, 1.6 into 10 to the power of minus 19 coulombs. Tau is the average collision time, the time between successive collisions. Okay. M is the mass of the charge. The charge is electron, the mass of an electron. Okay. Because sigma and rho are related by sigma into rho is equal to 1, therefore rho turns out to be equal to the reverse of this, m upon n E square tau. Where we consider that for the under the given set of conditions that we have, the tau and n are considered as constants. They are not valid. Okay. So for a material, the conductivity and resistivity are defined in terms of the number of electrons per unit volume, the electronic charge, the average collision time or time between collisions, and the mass of the charge, which is electron. Okay. So that is why I am saying that this is okay. Now we define another attribute. That another attribute is called mobility. Again, ETVT, EVT, TVT. So, mobility. How much mobile is the charge? The mobility is measured and is defined like this, that is Vd upon E, but in fact, by the systems approach, I will say that my Vd is proportional to E, and therefore Vd turns out to be equal to constant times E. Okay. Where mu is neither a function of E nor a function of Vd. Okay. So we have this, and we can work out the unit. Velocity is meter per second divided by E, which is volt per meter, turns out to be like this. Okay. This is the electron mobility. Why do I say electron mobility? Because there is another kind of carriers, charge carriers, in the case of semiconductors, and we term them, we give them a name, and the name is hole. So there is electron mobility, and then when I am talking about semiconductors, there will be hole mobility also. Normally at the same temperature, if electrons and holes both are present, then the electron has more mobility as compared to holes. Anyway, so I can write this mobility mu is equal to Vd upon E, and put in the value of Vd which we obtained before like this, okay, and put it here, and E and E will cancel out, turns out to be equal to E tau upon m. Okay, this mobility turns out to be equal to E tau upon m. So this is the value of the mobility that we obtain, E tau upon m. Okay. Now you can see that E upon m for the electron, E is a constant, m is a constant, and E upon m is also given a name, a specific name for the electrons particularly, and this was once upon a time called the specific charge of an electron, the ratio E upon m. This is what was first of all determined before the electronic charge could be determined. We determined in an experiment E upon m. Okay. So you can find from here that E upon m is a constant, so mu is proportional to tau, the average collision time. And if by the system's approach you know that if I plot mu versus tau, if we are somehow able to determine the mobility and the average collision time, then I'll get a straight line graph whose slope will give us E upon m. This is another way I can say. Okay. Now, after this, I must confess that the Ohm's law, where V was proportional to I and V was equal to Ri, does not hold always. There are deviations from the original law of Ohm, and this is because of things, materials and devices. So I must confess to you that for the last few hundred years, 80% of the research and the 80% of the research grants, which run into trillions of Indian rupees and millions of hours of dedicated work by scientists, engineers and technologists, has been to study the materials, the properties of the materials, the electrical properties, the magnetic properties, the thermal properties, various kind of properties associated with it. So there is a deviation, and I show you the deviation in VI curve for conductors. Okay. What happens is, actually the curve should have been a straight line, which continues as the dotted line here. But the material is such that, the activities are such that, the events are such that, the behavior is such that there is a deviation. And this is what the deviation shows. That after a certain amount of current, the behavior becomes different from what is Ohm's law. Okay. So, certain conductors. Okay. And what does it mean? A material. Material is a device. Okay. It can be a wire, it can be a block, it can be anything. I can apply a potential difference between these two and the current will pass. The potential difference we know, the current we can measure with the help of an instrument called ammeter, and we can conduct the experiments. After the conductors, then comes the beauty of a device which is called a diode. Diodes, they behave like valves. What happens is that in this direction, the current will flow, which has been shown by an arrowhead, easily. That is, the resistance offered by the diode is very small. But in the reverse direction, if we make this positive and make this negative, oh my God, then the resistance is too high. So current is allowed to pass in one direction and is blocked in the other direction, or the current which flows is very, very small. Diodes, first of all, historically they came as what is known as cat's whisker diodes. Thereafter the diodes were in the shape of valve, and then the semiconductor diodes came, and for normal semiconductors, I told you that the conductivity of the semiconductors is between those of the good conductors and the bad conductors, the conductors and the insulators. Okay. So anyway, now this diode that I have shown to you in the today's solid state electronics, these diodes are normally made of silicon. Okay. materials n-type and p-type, and if the p-type is made positive with respect to the n-type, then of course there is flow of electrons and holes. And in one direction you can see that the current changes as the potential differences increase, the current changes like this. You can see that the current is in milliamperes. In the reverse direction, when this side is made positive and this side is made negative, there is a very, very, very small current, microamperes or nanoamperes. And then, of course, there is a breakdown and the value of the current, it increases. There will be occasion to talk about these devices in detail later on. Okay. So, the elemental semiconductors, which are elements, they are silicon and germanium, mostly. And silicon, which is the most abundant element, silicon dioxide, you know, it's the sand. From that material, then we can have semiconductors which are made by mixing group 3 elements with group 5 elements, like gallium arsenide, gallium phosphide, okay, etc., etc. Other semiconductors are also made where there is a chemistry of the group 2 with group 6, 2,6 semiconductors. There are other semiconductors which are organic materials. All of them, they are studied by the same technique, making a block, making a connection with the metal on both sides, and then passing the current, measuring the potential difference and passing the current and measuring the current, etc. Now, here is a very interesting thing which you can see, that as I increase the potential difference, then what actually happens in this material is that initially we have a linear behavior. Thereafter there is non-linearity which comes into the system, and then it reaches a peak. After that peak, the value of the current keeps on decreasing. Okay, the value of the current keeps on decreasing until a value point is obtained, and thereafter it again starts increasing. Now this region number 3 is called the negative resistance region. But the resistance has to be defined. The resistance has to be defined not as V upon I. If you define the resistance as volts upon amperes, then it will be positive. But dV upon di, if we define it as dV upon di, okay, that is, we also sometimes call it a dynamic resistance. And this resistance V upon I we call static resistance. So it can never happen that V upon I is going to be negative. But dV upon di, as you can see, because when I, at this point you look here, and if I make it, then I is decreasing when V is increasing, which is shows negative resistivity and negative resistance. We talk more about it. So continuing with what we are doing about resistivity, now we'll talk about resistivity of materials. Resistivity of materials is maximum for the case of insulators, then for semiconductors, and then metals and specially designed alloys, etc. These are normally available in any of the books in a tabular form, and you can look at that. Then resistors are normally made of certain alloys like nichrome here, okay, which has special properties with respect to temperature dependence, etc. But there are some resistors, and resistors have also some ratings, how much current they can tolerate. So that kind of toleration we can study later on when we talk about the energy, etc. in resistors. Okay. Now there are resistors which work at low currents, okay, and they are called carbon resistors. They are normally film kind of resistors, and they can be made with hand in homes, cottage industries, but the value has to be given. So how to give the values? Then somebody suggested a color code. Color code is a decimal base system. If we have this as the resistor, okay, then there are some colored disc lines all over the material, and which I am calling A, B, C. Then there is another strip over here of color which is normally silver or gold, and sometimes it's missing, so I'm writing it as 0. Okay. So when we have these colors, any color like that, we write it like 23 into 10 to the power of 6 C, 2 into 10 to the power of 4, like that, etc. And these colors indicates the accuracy level, which is called tolerance. Okay. If it is missing, then the tolerance, that means inaccuracy, will be 20%. If it is silver in color, then it is 10%, and the best ones are 5%. Of course, there are when the accuracy is a big factor, then even resistances with a tolerance of 1% or 0.1%, etc. are also designed. But as the tolerance level decreases, the cost of the resistor becomes larger. Okay. Here the colors are black, brown, red, orange, yellow, green, blue, violet, grey and white. And they indicate numbers 0, 1, 2, 9. Okay. Black, B, B, R, O, Y, G, B, violet, green, grey and white. Okay. Some people think that the black was relegated to number 0 by the white people who took the number, doctor's order number 9, okay, as white. The number 8, 2 fat majors, grey. Then violet, blue, like that. The number was decreasing order. How do we remember that? Then somebody, he told us it's better to remember it like this. There was one Mr. B.B. Roy, R.O.Y. He went to Great Britain, from where he got a very good wife. Okay, so this is gender centric. I don't subscribe to that. Anyway, it's a good method of remembering these numbers and looking at the tray of resistors, we can find out the value which is required by us, etc. This is very simple thing. Okay. Well, very good. Why if I have objections? Because Great Britain is famous for its houses. The US is famous for its fat salaries. Okay. And it is said that the best food is available in the Orient. India, Pakistan, Bangladesh, Myanmar, China, even Japan. But it is said that the wives are very good. Number one, Germans, Austrians, and then Egyptians also. Okay, maybe. It doesn't matter. Now we talk about another aspect of resistivity, and that is temperature dependence. Well, what will happen? That as the temperature is increased, so the electron motion, there will be vibrations, and the resistance or resistivity will increase in the case of metals and alloys. Because in the case of metals and alloys, the number of electrons per unit volume with temperature, it hardly changes. There is no change. But this is rho T at temperature capital T, rho naught at a temperature 0 Celsius, T Celsius, 1 plus alpha. Alpha is called the temperature coefficient of resistivity. You can also say, if we find out, it's also the temperature coefficient of resistance is also the same temperature coefficient of resistivity. Anyway, so we find the alpha. This alpha could be positive. It is positive for the case of conductors because the electron motion is becomes more disturbing and there is less order at higher temperatures. But in this case of semiconductors, interestingly, the value of alpha is negative. So the resistivity decreases with temperature for a different reason. Okay. In the case of semiconductors, I told you, besides electrons, there are holes. Okay. And as the temperature is raised, so there the number of electrons and number of holes that increases, and that does we'll have occasion to look into it when we are talking about the semiconductors. Okay, exponential. So in the case of conductors, metals, alloys, etc., the variation of rho is like this. But for example, I have shown that in the case of a special material out of which wire resistances are drawn, it is a straight line like this. Okay. At a temperature 0, it's some value, and then etc. etc. In the case of semiconductors, the rho value keeps on decreasing. Okay. With temperature. Conductivity, sigma, naturally in the case of conductors will increase. In the case of, it will decrease in the case of metals and alloys. In the case of semiconductors, it will increase. The conductivity will increase. And nichrome, of course, it shows that the conductivity is changes, but slowly and gradually like that. So these are some of the factors, some of the things which are associated with this. We'll have occasion to talk more about this dependence, etc. Okay, and we'll talk in the next lecture the beauty, that is what happens to the heating effect in resistors and how energy is generated and dissipated in the case of resistors, not like in the case of the capacitors where the energy is stored. A resistor is the Raja Beta. The resistor is the Raja Beta, is the king of Tartary. Whatever you give to the resistor in the form of an energy which is created by V and I, it will always spend it, never store it. And the capacitor is like the mothers in the house. When I give my wife 50,000 rupees to spend for the month, then she will always save a couple of thousands or sometimes even 10,000 and put it somewhere, okay, as a saving. Not like that exactly, but capacitors are energy, storage, and then you can take energy from that. But in the case of resistors, whatever energy is generated is dissipated. We talk about that shortly in the next lecture. Till then, bye. Ni hao.